Introducing, well, he was already introduced yesterday, Erwin Frey from München, who's going to tell us more about game theory, and I, for one, am very interested in hearing this. Please.
Thank you very much. So welcome back to my lecture. I'll continue where I stopped yesterday. That was on two-player games in this general setting where if you would have cooperation, you get a reward. If you both defect, you get punished. And if you defect and the other one cooperates, you tempt it and you gain a temptation, and otherwise you get a payoff. We already said that you can reformulate this game also in terms of so-called replicator equations, which are to some degree arbitrary. And the way I set them up is to say that the rate of increase of the individuals A is given by the surplus of their fitness as compared to the average fitness. That's the equation on the board. So now we just plug in what we know about those two quantities. Just take for the fitness of individual A, R times A plus S times 1 minus A. That's how it was defined, and subtract from it the average fitness. And what you get out is a formula which lends itself to a very natural explanation. You have a product A times 1 minus A. That's just the probability of individual A and B meeting. And then you say that the rate by which the population increases is given by the fitness difference of individuals A and B. Now you have to plug in here the explicit expression for fitness of species A and species B. You can easily do that, simple algebra. And then you find this expression where the quantities mu A and mu B are now defined in terms of the entries of this payoff matrix. Mu A is S minus P and mu B is P minus R. And if you put this in terms of a new payoff matrix, the meaning is as follows. Mu B is the advantage of playing strategy B as compared to a strategy A, and vice versa. Mu A is the advantage of playing a strategy E if the opponent is playing strategy B. This is an equivalent form of the payoff matrix here for the replicator dynamics. In general, it is not, because I'm not in generally getting the differences of these payoff interests into my equation. But once we are there, we can also define a very simple game, namely where we say mu A and mu B are both equal to 0. That's a neutral game, and actually has an application. It's the Fisher-Wright model of population genetics. Same kind of thing. Okay, so that's what you get out, and now we can start classifying the model simply by the signs of these entries, mu A and mu B. So let me go to the next slide. So here we have the payoff matrix again, and now you can distinguish 4 different cases according to the signs of mu A and mu B. Let's take the examples which we know already, which was the prisoner's dilemma and the snowdrift game. In the prisoner's dilemma, mu A was less than 0 and mu B was greater than 0. That meant that this here is actually a Nash equilibrium, and deviating from it, you actually lose. In contrast, if we look at the snowdrift game, mu A here changes sign from negative to positive, such that for an individual it pays to play the opposite strategy of your opponent. So now that structure that goes on with other signs of that particular entry of the payoff matrix, but the important thing is that these signs here translate in a very simple structure of nonlinear dynamics. So let's go back to the equation here. What we have there is really a general equation for a nonlinear dynamics in one dimension. And such an equation in one dimension, you find this, for example, in the book of Stochastic, has only two different types of ordering elements in it, namely the zeros of f1a, and the zeros could be attractive zeros or repulsive zeros. Now let's look at the various cases which we have here. Let's look at the prisoner's dilemma game first. So here I have an overall factor which is a times 1 minus a. So that would be a structure which looks like this. If I put here a, here 1, here 0, here f. And now let's look at the signs of mu of a. The signs are such, let me go back, see what it is. The signs are such that mu a is actually less than 0 and mu b is larger than 0. Sorry. So you have here mu a less than 0 and mu b larger than 0, and that means that this expression here is actually negative for all values of a. It varies a little bit with a, but it's essentially negative. So the curve you get is something like this. And that means that the value of f is always negative in the whole parameter range. So you have a minus sign here on the right-hand side. That means the change in a goes to the left. So this here is an attractive fixed point, and that here is an unstable fixed point. Now let's look at the other case, which was the the snowdrift game. In the snowdrift game, mu a is positive and mu b is positive, so both are now positive. Look here, this here is a positive number, but since those two signs are different, there's now the possibility of a sign change in the interval ab, and actually there is. So the structure of that function looks now like this. As I go from 0 to 1, there is a point where f of a crosses 0. Same kind of argument. Here you have a positive value of f. The flow goes this way. Here you have a negative value of f. The flow goes that way. So we end up with a stable fixed point here and two unstable fixed points there. We see now in that language of nonlinear dynamics, the concept of Nash equilibrium simply translates into stable fixed points. Nash equilibrium for the prisoner's dilemma were all defecting. That's now the fixed point of nonlinear dynamics. Here for the snowdrift game, you have no unique Nash equilibrium for a game where you play strategy A or B with certainty, but you do have actually a Nash equilibrium if you play strategy A and B with certain probabilities, and then this fixed point here corresponds to a Nash equilibrium with probabilities for the strategies. Okay, the other cases are similar. I think I don't have to put them on the board. Let me just mention the one case where actually I can draw really anything where f is identical to 0. Here you have a line of fixed points, meaning no state is actually preserved, but still you do have absorbing boundaries here at 0 and 1. So it's not simply a random walk in that case, it would be a random walk with absorbing boundaries. Okay, so now let me study next those cases here in a stochastic setting, so you get a feeling of the effect of stochasticity in that problem. So we can switch this off if you like. I don't know how it works. That's the take. Would that work? It's just a flex.
It's good.
Okay.
No, you need the light. You need the light.
I need the light.
You need the light.
Yeah.
This one? No.
Okay.
Switch off that. Yeah.
Okay, so we have different scenarios for those deterministic games, and now let's talk about the effect of stochasticity. I will do so in a rather elementary fashion, but as you will see, with that I can just define three very generic cases which will reappear in later stages of my talk. So let's take as the simplest example just a linear death process. That means you have a population of size n, and at some random times you go over to a population with one individual less, and you do so with a certain rate lambda. I think you heard about this already in Sid Redner's talk. You can set up for that a master equation with some right-hand side, which I don't even write down since I think you know how to do that. There's actually a simpler way of analyzing that problem if you are interested only in certain quantities. And the quantities I'm interested in is the time it takes for the system to reach the absorbing state, so to reach a state where n is actually 0. That's the time I would like to know. Starting, of course, from some initial condition where n would be some initial population size n. Okay, how would I do that? Well, define a quantity q of t, which is the probability that a given individual at time t is alive. Okay? For that quantity, I can look at the probability that this individual is still alive at some time later, at some time t plus dt. The equation for that is clear. This is a Markov process. So the individual has to be alive at time t. That's q of t. And I have to multiply this by the probability that during this little time interval dt it did not die. And that's 1 minus the probability of dying, which is the rate times the time interval dt. That's a very simple argument. And now you Taylor expand the left-hand side, and what you get is an equation saying that the temporal derivative of this probability is minus lambda times q. This equation, of course, you know how to solve. The solution of that is q of t equals 1, because the initial condition is that the individual is alive at time equals 0, so q of 0 is 1, and you multiply this by the exponential of minus lambda times t. So what we learn from that are two things. First thing is that the typical time for this individual to stay alive is given by 1 over the death rate. And the second observation you make is that the times are actually exponentially distributed. This simple observation, actually, that time scales are given by 1 over rate and they are exponentially distributed, is at the heart of what we got yesterday, is the kinetic Monte Carlo Wojcicki algorithm. Okay, I can learn more. I can ask now, what's the probability that a population, not an individual, but a population of size n, continues of that size for a certain time period? And then I have to multiply what I have here for one individual just by the total system size n. So this number here then is given by tau over n. Since each of the individuals has the same chance of dying, so that reduces the survival time of the population of being of size n. So during that time period, the population size changes from n to n minus 1. Well, now I'm ready to write down the time it takes for the system to die out. I simply add up the times it was of size n naught, it was of size n naught minus 1, etc., plus t of 1. And that's the time it needs to get extinct. I can write this as a sum from n equal 1 to n naught over 1 over n multiplied by my basic rate constant time scale r, or 1 over lambda. Of course, you can sum this exactly. This is something known, but all we need here is an approximation. So I replace this by an integral from 1 to n naught, 1 over n dn, and you see this integral is the logarithm of n naught. That's one very important conclusion. If you have a dynamic system which drives you towards an absorbing state, like here in the linear death process, the time to extinction scales as the logarithm of n naught. That's not only true for this case here, it's true for that case, and it's true for that case, it's true for any case with a stable fixed point. Okay? So remember this. This is a very important result which will show up in a second again. The next scenario I will look at is as simple. It's now this case where I study a linear death birth process where there's no preference for ending up at state 0 or state 1. Okay, for that, if you write down a deterministic approach, it would look extremely simple. It would just say I have a death rate lambda, but I also have a birth rate, which now enters with a different sign, n of t, and since I want it to be neutral, lambda would be equal to mu, and nothing would happen in the deterministic dynamics. You know that's of course not true, because there are stochastic effects, and now we would like to estimate how large those stochastic effects are. Okay, now I really have to write down a master equation for this linear death process. It contains, as you know, processes which lead to a gain and a loss in the probability of having a system of size n at time t. The gain comes from populations of size n plus 1 with a rate lambda times n plus 1 multiplied by the probability to be in that state. You also get a gain from states same lambda, which are one particle less, now by a birth event with the same rate lambda, times the probability p of n minus 1 and t, and you lose in both directions. You can lose to n plus 1 or n minus 1 if you are in state n. So since you're losing in both directions, you have a factor of 2 times lambda times n. Now I know you can solve this exactly with generating functions, but that's not what we want to do here. I want to look at this equation in a very simplistic way and just Taylor expand the expressions which we have here. So I look at the expression n plus minus 1 times n plus minus 1 and t, and simply, without caring too much about the mathematical feasibility of that approximation, I write down a Taylor expansion of this expression. So that would be n times p of n and t, and I would add plus or minus the derivative with respect to n of the same expression, n times p of n and t, and plus a half times the second derivative of n times p of n and t. Now you plug this into the equation, the master equation, a line above, and you'll see that the terms here, which are linear in the derivative with respect to n, but also this term here, they completely cancel out of the equation, and you get a very simple equation reading dt p of n and t equals the rate lambda times the derivative with respect to n times n p of n and t. And you take the derivative of the whole expression. Now let's normalize our variables here. It makes sense to talk about the fraction of particles compared to the initial size, which I take as n naught, and rewrite the equation in terms of that particular frequency. And then you have dt p of x and t equals a diffusion constant times the derivative with respect to x of p and x and t. And from the scaling, you immediately find how diffusion constant depends on your system size. And the important conclusion is that the diffusion constant is lambda, but that's more important, is lambda divided by n naught. So you learn here that the effect of fluctuations in the system is one-to-one correlated with the size of the system. As the system size n naught goes to infinity, your noise, that means your diffusion, actually goes to zero in this particular fashion as 1 over n naught. That's one thing you learn. And the second observation one makes here is that all time scales actually scale in the same way. The time scale here all scale as e to the minus 1 simply by looking at the scaling of this equation. So that means including, the extinction time here, this also scales as a time. So that means my extinction time is proportional to e to the minus 1 is proportional to n naught. So, in a moment. So, in distinction to that case, where you have an attractive fixed point and extinction time scales logarithmically in n naught, for the neutral case, you have an extinction time which scales as the population size.
And in the initial system had a particle pole symmetry, right? The absence of an organism is equivalent to an organism. But your equation now has x, and it's not symmetric if I change x from x.
Yes.
So that should be mistakes in that way.
That could well be. You're right. I think I mixed something up. Oh no, sorry. I was misleading you. This here is the process where you have two absorbing boundaries. This here is not the same problem as that one. That's a linear birth-death process where the only absorbing state is n equals 0. So that's not the same. Yeah? If you would have this particular case, you're completely right, then instead of an x here, you would have x times 1 minus x. That would not change the conclusion in any way, because your time scale still would behave as e to the minus 1 proportional to n naught. But thanks for asking. Okay, so remember those two things. Now there's an alternative scenario, which I didn't put down here, but there is another set of parameters where you actually have a bistable system. That was this game where you would, it's called matching pennies. Here you have, instead of a stable fixed point, you have an unstable fixed point in the middle, and then you have stable fixed points here at the boundaries. In that case, you are still in the regime that if you are here and going that way, it would take you a logarithm in n naught, and here the same way. But if you would be asking what's the probability of being here and ending up at that state, then you would need to cross a barrier, and crossing a barrier is similar like in Arrhenius law. Then you take a time which is actually exponential in the population size. So if for some reason in my population dynamics the drift is such that I'm pushed to the middle and I'm asking how I'm getting to the outside, then the extinction time for that case would actually scale as the exponential of n naught.
Excuse me, so now your big T here, this is average extinction?
It's always the average extinction time. I'm not talking about distribution of extinction time. So if I write down T, I mean by definition that this is the average extinction time. Yeah, I define it this way. Already by writing this here, I say the average extinction time is the sum of the averages of times it takes to go from population size n naught to n naught minus 1. So I always talk about averages, never about any kind of distributions. You could do so, but that's not important. So remember, if you have a dynamics pushing you towards the fixed point, like in this case here towards the boundary, or in that case towards the boundary, your extinction time scales logarithmically in n naught. If you have a neutral dynamics, the extinction time scales as n naught. And if you're asking, like here, what's the probability of getting extinct to here, or in that case, the probability of getting extinct, in both cases, you need to cross barriers, and then your extinction time actually scales as the exponential of your initial system size. Okay? So with those three scaling arguments, I will now go and discuss some of the game theoretical problems, and for that I need the projector again. Okay, so we're now talking about well-mixed populations, and the example I want to give is the Rob-Sister paper game. And we're not going to analyze this mathematically, but really in terms of these simple scaling arguments. So I told you already, the game is defined by these three reactions, where A and dominates B, B C, and C back dominates A. In a Bern model, where you keep the population size constant. In the deterministic formulation, I have this on the board. We have this set here of rate equations. This set of rate equations has a constraint, which is the fixed population size, meaning that A plus B plus C is equal to 1. Because that's the case, you can represent the dynamics of a problem on a simplex, where here on that axis, the left point is is A equal to 0, the right point is A equal to 1. On that axis, here is B equal to 0, here is B equal to 1, and here the same for C. You already see circles. The circles have a reason, like in the Lotka-Volterra model. There's a conservation law, and the conservation law here is just the product of the population sizes for A, B, and C, each of them multiplied by the respective rate constants Kb, Kc, and Ka. That's why you have circles. You have three organizing points, you have three absorbing fixed points, and in the middle you have one reactive center fixed point. So the important observation you should make here is that you do have circles. That means that the dynamics is on a completely flat landscape. There is no force pushing you into the direction away or towards the fixed point or away or towards the absorbing boundaries, unless you are at the edges of the simplex here. So that puts this example here into the neutral process where I have an extinction time proportional to n naught. Question?
So, did I miss something, or did you explain why the center fixed point is not in the center?
The rates here are generically all different.
And so that if they're all equal, that puts it directly in the center, and if they're different, then that shifts it to various points in the
Okay. So you can say by tuning those parameters, you can push these lines here closer to this edge or that edge or that edge. It has an important consequence, as you will see in a second. But for now, say, put yourself in a position where you would move this in the center, and then there would be no preference for one edge or the other. Okay, so important observation, this is completely neutral dynamics, it's like a random walk, and the only thing which distinguishes it from a random walk is that on the phase plane of individuals A, B, and C, you have cyclic motion along constants of motion of this particular system. Okay, so that would mean, going back to my experiment, where we studied the 3 strains of E. coli, that if the population size is large, then I should actually observe oscillations in the number of bacteria, which I don't. What one observes is that one species dies out, the second one dies out, and the other one remains. The reason for that is that you do have stochastic dynamics and not this type of deterministic dynamics, because you have finite population size, and you see this in a second. If you go to stochastic evolution, then you have a random walk on the phase portrait. On top of this circular motion, if you project this out, you just have a random walk with some modifications. The diffusion constant gets a bit smaller here at the edges, but essentially you have a random walk. And then it happens what must happen. At some point you hit the boundary, and once you hit the boundary, you have 2 players left. Say scissors playing against paper, and then scissors cut the paper, and you end up at one of the absorbing things. And the time it takes, that you can just take from the simple calculation, is proportional to the system size and not. And if you want to know more about the system, what you have to do is, of course, you have to set up a proper Fokker-Planck equation in terms of a Carnot-Moyal expansion. I think you've learned how this goes. And with that, you can actually calculate more. You cannot just calculate the typical extinction time, but you can also calculate probability distribution functions and things like that. Okay, so let me come back to your question. What happens actually if you consider a system where the rates are unequal? Something funny happens actually. So look at this graph here again. Here is one of these periodic orbits corresponding to the constant of motion. And as you notice, these periodic orbits have a closer distance here to that edge than to the other 2 edges. So the question now is, what's the probability of ending up in a absorbing state where you would have only A, C, or B individuals? Is there a smooth crossover as I increase the system size, or is there something interesting happening in that particular deterministic limit?
Are these the same lambdas that you had on the board?
Pardon? No. This is just now numbers characterizing the distance from this outermost part of this orbit to one of the edges. And lambda B and lambda C here are chosen such that the distances of this orbit here to the edge is the same. That's just a choice of parameters. And the closest distance you have is actually to the edge where A competes against B. Yeah.
So before you go on, going back a slide, I just wanted to ask you something about the Kramers-Weil expansion you mentioned.
Yeah.
So suppose you weren't just interested in the hitting time, suppose you were interested in the evolution of the entire Fokker-Planck equation.
Speak up.
Suppose you were interested in the evolution of the entire Fokker-Planck equation and not just the hitting times. So you mentioned you have a Kramers-Weil expansion, but you also have extinction events. Could you go over some of the techniques for dealing with degenerate diffusions in that kind of situation? So when you're getting a diffusion coefficient for one species that's going to 0, what are some tricks that people use for overcoming that problem? If you're interested in the evolution of the entire probability density.
I mean, it's very straightforward. I can tell you that. What you do here is you write down the master equation for the problem, and you do a Kramers-Weil expansion in a straightforward fashion. So we go to
the small diffusion coefficient doesn't cause problems then?
No.
Okay.
No. Because diffusion also goes to 0 at the edges, but that doesn't cause a problem. The only thing which causes a problem, where you need to think a little, is how you eliminate the motion on those periodic orbits, how you get an effective diffusion equation for a system where the variable is the constant of motion describing the orbit on which you're on.
So, I guess, I can talk to that.
But there's really no problem here. In general, if you hit an absorbing state, you should worry about what happens at the boundaries, because there you have low copy numbers, and then a Kramers-Weil expansion is in trouble. So you write in that, but for that particular case, it doesn't matter. Okay?
Or is this,
this is technical. Okay? If you have a system where it takes a long time to reach the absorbing state, and your power law dictates towards the absorbing state, then you need to worry about how to describe the noise in that long time asymptotic limit. Here you rather fast at the absorbing state, and the last second, so to say, to hop from here to there, that doesn't really matter.
So is it correct that you can write a closed equation for capital K?
I can write down a closed equation. Which would read like dTp of K and T with a drift and a diffusion term. And there is a mathematical way of doing that. You eliminate the fast degrees of freedom, then you get an effective diffusion, effective drift. What's interesting about those equations is actually that from the noise, you get a contribution to the drift. And what could happen there is, say imagine you have a system where you have an absorbing, where you have a center, so the flow goes to the middle, but you have fluctuations in the system, and also some kind of periodic orbits. By deterministic dynamics, you would conclude the system ends up at the absorbing fixed point. If you now include noise, what noise does is it's constantly pushing you out of the center. And now eliminating the stochastic dynamics on the periodic orbits, you get an effective drift. And with that effective drift, you have an equation which actually has a limit cycle, which is not caused by noise. But let's come back to think about this more intuitively, not mathematically. So here, how should we think about this intuitively? Well, here, in this linear depth process, if I want to derive this result here, that T is equal to ln n naught, I could take a shortcut and could write an equation for the population. I could just simply write n of t is equal to n naught e to the minus lambda t, which is deterministic dynamics. And I could estimate the extinction time by saying, when is this n of t equal to 1? Because then the probability is very high of getting into the extinct state. And if you do that, you see that immediately you get the same result. You can do the same thing here. You can ask, you can take the orbit as the extinction orbit, whose closest distance to the next edge is actually one single particle, or one single particle change. And that's the orbit I've chosen here. So here you have a random trajectory which is pushed by the noise and the deterministic dynamics on this outermost orbit, which has only a distance 1 to this edge here. And that's then, so to say, the most likely path the system will take to die out. And from that, you can estimate the probability of ending up in this state and ending up in that state or that state. And what you find out is that the probabilities of ending up in those states here, C or B, is actually suppressed against the probability of ending up here by a certain power in n. And that means the limit n going to infinity, I know for certain that all stochastic trajectories will go to one particular state in the end. And funny enough, that's just looking at the numbers, it will be the state which actually has the lowest growth rate. So looking at my E. coli game, where you have the colicin-producing species being the most dominant and killing off the sensitive strain, the weakest one with the lowest growth rate was the one which is actually resistant. And that's the outcome of the experiment. In the experiment you saw that the resistant strain is the one surviving the game, and that comes out from this stochastic analysis here, also for the rock system paper game. Okay. So what I want you to remember from this short intuitive way looking into the stochasticity of game theoretical problems is these three scaling laws: logarithm of n, proportion to n, and exponential in n. For the rock sister paper game, I have a neutral dynamics, so the time to extinction is n. And as I just explained, the game is such that the one with the lowest growth rate, which I call the weakest, wins the game, and that's the experimental outcome. So that explains the first part of this care experiment, where the resistance strain is the only one surviving this particular game. Okay, how am I doing in time?
You have 15 minutes left.
15?
Yeah.
Okay. Good. How do I do this? Well, I start then. So what I want to do next is now I want you to learn something about nonlinear dynamics, such that in my third lecture you can understand the combined effect of stochasticity and spatial dynamics for this rock sister paper game. And I will discuss this in a bit more mathematical fashion, but it's important since it really leads to an interesting set of concepts which you can apply in quite generality to all kinds of nonlinear dynamics problems. So the idea is really to teach you something about how you can simplify a given nonlinear dynamics problem. Okay, let's start. In case I'm getting not through, I will continue then tomorrow. So the idea is now to look at cyclic dominance. And what I will discuss is a particular model which is called the May-Leonard model. It is different from the rock sister paper game in that it is a two-step process. It has one selection step, and the selection step is that if A meets an individual B, it's not immediately replacing the individual B, but at first it is simply killing the individual B and generating an empty site. And that I want to happen with a selection rate sigma. And of course you can repeat this with B plus C going to B plus 0, C plus A going to C plus 0. The next step is a reproduction step. And I want this to happen with a birth rate mu. And here the rule is if A is next to an empty site, then it may give birth to an individual A with this birth rate mu. And of course, the same I do for each of the other two species, B and C. So now if I go to the limit that Ni, meaning for I equal A, B, C, is much, much larger than 1, I can neglect stochastic fluctuations, and I write down again a set of deterministic rate equations for nonlinear dynamics equations. Those rate equations are simple to write down. So A dot, which is the temporal derivative of A, that's the selection process plus the reproduction process. The selection process, I put down first the reproduction process that happens with probability A times finding an empty site. Finding an empty site is 1 minus rho, where rho actually is the sum of all the fractions of individuals of species A, B, and C. And I multiply this by my birth rate mu, and I have to subtract from here the case where an individual C meets an A, and that happens at rate A times C times the selection rate sigma. And of course, you write the same kind of equation for B and C, simply replacing in a cyclic fashion A by B and B by C and C by A. So together, this gives a set of equations for a vector variable, a vector given by a vector function depending on the state vector A, and my definition of A is just A, B, and C. So and once you're there, once you have an equation which is of this structure, there is a standard set of steps by which you analyze this nonlinear dynamics problem. And I will explain that to you. First, let me draw the phase space. So what we want to solve is this equation. A vector dot is f of A. This is for a three-dimensional state space now, where I have individuals A, B, and C. And as usual, any kind of nonlinear dynamics is organized in phase space by fixed points in what's called invariant manifolds. The fixed points I have are absorbing fixed points. These are either R0, that's one absorbing fixed point, only A, only B, or only C. Those are the 4 absorbing fixed points. In addition, if you look numerically at that equation, you see there's another organizing geometric object, which is an invariant manifold, which looks roughly like this. So it connects the absorbing fixed points where you have only individual A, C, B, or A. And in the center of this invariant manifold, where invariant manifold means that if you have a trajectory starting on that manifold, it will stay there under this dynamics. So in that manifold, you have a reactive fixed point, or also called coexistence fixed point, since it describes the simultaneous presence of all 3 species, and in contrast, those fixed points here are the absorbing fixed points. A typical trajectory on this invariant manifold looks like that. The fixed point here is unstable. The trajectory spirals out, goes to the boundary, and then moves from one absorbing fixed point to the other in what is called a heteroclinic orbit. What that means is it goes from one point to another point to another point to another point. That's what heteroclinic means. In essence, if you project out a periodic motion on the periphery, this is more or less an exponential decay towards one of the fixed points. A bit of a caveat, since the time it spends here and there is increasing with growing time, but essentially it's an exponential decay. So from that, just from the numerics of that, you would conclude, well, now if you have empty size in the problem, the typical time for extinction scales as a logarithm of n naught, since you have a deterministic drive towards the absorbing fixed point. Okay, so what are the steps now to analyze this problem? It's kind of obvious. So there are 3 steps. The first one is, of course, you want to be at the fixed point. So the first step is you define a new variable, which is A minus the reactive fixed point, which I simply call A star. And you rewrite your equation in terms of this new displacement variable. So you write x dot equals f of x plus A star. And now forgive me not to write the vector errors. I think that's clear from now on that those are vectors. You can Taylor expand that. Then you get as a leading term the Jacobian at the fixed point plus a term g of x, which contains all the remaining nonlinearities of the problem. And since the problem is so simple, as you see on the right-hand side, the only terms which this nonlinearity contains are quadratic in x. What I mean by that is that it contains terms like xa times xb, xa squared, etc. This here is the Jacobian. I simply call it A. And the first thing you want to do is, of course, you want to do a linear stability analysis close to that fixed point, so you reduce your equation to a linear equation. Well, I don't write down, I missed this, sorry. So I don't write down A, because it's just tedious to write all the matrix entries of that. What you gain in doing the usual thing, you determine the eigenvalues and eigenvectors. You find one eigenvalue lambda naught, which is negative, given by minus the birth rate, and you find two other eigenvalues which are complex conjugate pairs, C1 plus minus I omega, where the constant where C1 and omega are constants, and they're given by my selection and birth rates. And in order for you to have some kind of intuition about what those numbers are, C1 is mu times sigma divided by 3 times birth rate plus selection rate, and omega is square root 3 over 2, the same expression, birth rate times selection rate divided by 3 times birth rate plus selection rate. So this tells you there's one stable direction. If you compute the eigenvectors, you realize that this is actually the diagonal pointing this way. Yeah. So, and I call this my direction 0. So all the flow is sucked along this unstable, stable direction onto this fixed point, or if you're somewhere else, onto this invariant manifold. And on the invariant manifold, you have a complex set of eigenvalues, and that means you have an unstable spiral, since C1 is positive and omega is also positive. So this here is an unstable spiral. Okay, now, once you know this, the next step is to transform this linear problem to the simplest form you can imagine, given those kind of eigenvalues. It's a bit more complicated than for a symmetric matrix, because you have a complex set of eigenvalues. What you do is you transform to Jordan's normal form by a linear transformation to a new set of variables given by some matrix S. And the outcome of that is that the dynamics for this new variable y is j times y, where j is Jordan's normal form of my linear dynamics. It's SA s to the minus 1, and it is just the entries given by the eigenvalue, so it's C1 omega minus omega C1 0 0 0 0 minus mu. So in summary, the first step is you go into the reference frame of a fixed point, and then you rotate your axis such to have the simplest form for the linear description of the problem. And now, once you know this, you reformulate the full problem in this reference frame where the linear problem has Jordan normal. That's the second step. So I rewrite the nonlinear dynamics in the reference frame given by these variables y. That's lengthy algebra, but nothing complicated. What that gives you is that y dot is of course the linear part, j times y, plus the transformation of this nonlinear part into this particular reference frame, and that's plus s g s to the minus 1 y, and I simply call this a new function h of y, which has a complicated structure, but what you can tell, it's again just containing quadratic expressions in y. The reason is g was quadratic in x, and the original equation was also quadratic in x. So now what do you do with it? Now there comes a third really important step. Let me illustrate this graphically. So we go to what's called the normal form of the nonlinear problem. So let's imagine I go into the reference frame of the Jordan normal form. So that will be YA, YB, and YC. And that's then this plane here.
We are now on discussion time.
Okay, I finish this, takes 5 more minutes. So I go on to this reference frame. Here is the reactive fixed point, and the axis y0 is pointing out of the board. So we can draw this correctly. YA, YB, and this here is YC, corresponding to the stable direction. As you see in the way I drew it here, the invariant manifold is not really identical to this linear plane of the linear stability analysis, but has some curvature with respect to it. And for symmetry reasons, actually, one realizes it's parabolic. So something looks like this. So it's like a paraboloid shape which originates from the reactive fixed point. And what you really want is you want to project your dynamics on this invariant manifold. Okay? So you want an expression for the C variable as a function of the variables YA and YB, which describes this invariant manifold. It turns out that this here is just proportional, for symmetry reasons again, to YA plus YB squared, and algebra, tedious algebra, tells you what the constant of proportionality is. So now once you find out what YC is, you use this expression for YC as a function of YA and YB and plug this into this expression here. Okay? And then the outcome of that is an equation which puts the dynamics on the invariant manifold. So you have the dynamics of YA and YB being a spiral, C times YA plus omega times YB. Then here for YB, C1 YB minus omega YA. And the other parts I don't write down because they're complicated. They are functions f and g, and they will depend on y squared, y to the third, etc. And here the same, they depend on y squared, y to the third, etc. That already gives you a lot of insight, because now you have reduced the problem from 3 variables to only a set of 2 variables. And there's a next step which I don't do today. There's a way of simplifying this even further by doing a nonlinear transformation such that you can get rid of certain nonlinearities here in the functions f and g. And what turns out what you can do is you can actually get rid of the quadratic nonlinearities on the right-hand side. So let me repeat. It's a bit involved math, but it's very useful in the end. So you have a nonlinear dynamics problem. You have a reactive fixed point. You go to the reference frame where the linear analysis is the simplest. Then you rewrite your nonlinear equations in terms of these variables which are most suited for the linear analysis. And then, as a third step, you go to a plane which describes the invariant manifold, which I in the following call the reactive manifold, since all the interesting physics happens on this manifold end. Okay, thank you.
There are questions?
The idea for that last step is just, since you have a positive eigenvalue, you exponentially pass through them onto the invariant manifold, and so that's the Stochastic dynamics.
Yeah. You can also take language from RG. Would be the same. This would be the relevant the critical manifold in that sense. And here it's just a manifold where I know that the fast dynamics has already happened, and the interesting slow dynamics is on this invariant manifold. It's a lot of algebra, but in the end, the price is rewarding. What you get out in the end for the spatial dynamics is that you get a reduced description in terms of those 2 variables, which falls into the universality classes which are known from nonlinear dynamics. So what I get in the spatial case, for those who know, I get complex Ginsburg-Lambda equations. In order to find them, I really have to go through all the math here. So I know it's a lot of algebra, but as I said, it's important to do it this way. Otherwise, you cannot understand the system. Yes?
How do you get the invariant manifold to start out with?
The way, okay.
The one you drew on the left over here.
So, you know there exists an invariant manifold. There are theorems about nonlinear systems saying that you can partition the phase space into invariant manifolds. So you know there exists one, and then you can look for one. So what you do is you make the ansatz, as I said, this is a function of ya and yb. An invariant manifold means that the time derivative of yc on the manifold is the partial derivative of m to ya plus times the time derivative plus the derivative with respect to yb times the time derivative, all on the invariant manifold. So this is the equation which determines the invariant manifold M. And now the trick is that you realize that this mathematical problem which you have here is actually a linear algebra problem. And that's then the way you solve it mathematically. In the present case, it's pretty obvious how you do it, because for symmetry reasons, you see that n must be of the form of ya plus yb squared, plus higher nonlinear terms. So you use this as an ansatz with some unknown coefficient psi here. You plug it into this equation. You use the equations of motion, and then after some mathematical algebra, you're done. I would not advise you to do this by hand. Or maybe I would not advise you to do it only by hand or only by mathematics. You should do it in both ways.
What role of nonlinearity is played? It's linear analysis.
Yeah. The nonlinear, I mean, from the linear stability analysis here, is what you find is just a spiral outward, right? And it goes on a heteroclinic cycle. The nonlinearities here in the exact solution give you this heteroclinic orbit. Once we are done with this mathematical analysis, which is approximative, we will find that on the invariant manifold in the normal form, the problem actually has a limit cycle. This is not quite true, right? Because this is a heteroclinic orbit, but I find an approximative limit cycle. The limit cycle there is very important because in the end, if you look at the spatial dynamics, it gives you spiral waves from propagation, wavelength of the spiral waves, etc. So it really determines the kind of excitations you have in the spatial dynamics.
Anyone else? If not, then this.